Hello student. In the last lecture, that is in lecture number 9 of RCC design, we studied how to design shear reinforcement for a rectangular singly reinforced section. Now, this when a beam is subjected to any type of loading, there will be two actions. One is bending action, other is shearing action. For bending action, we provide steel at the bottom. You can see longitudinal steel here, which resists the tension, flexural tension, bending tension. As we know, concrete is very weak in taking tension. To assist concrete, we provide steel at the bottom. That is for bending tension. Now, whenever shearing action takes place, due to shear, there is a diagonal tension. And to resist diagonal tension, we must provide some reinforcement in the form of stirrups, either vertical or inclined, and bent up bar. Bent up bars are optional, but shear for to resist shear, the stirrups are very much essential. Now, IS code gives the recommendation regarding minimum shear reinforcement to prevent sudden failure and provide ductility to give warning of failure, to prevent premature failure if the bond to main steel is lost due to busting of cover, to act as tie for the beam reinforcement in position, and to confine the concrete. Means if there is zero shear force, this is imaginary case. If there is zero shear force, you will have to design minimum shear reinforcement in the form of stirrups where the spacing of stirrup is 0.87 Fy ASV upon 0.4 B. Here Fy is the grade of steel used for the stirrups, B is the width of the section, and ASV is the cross sectional area of the stirrups. How you will calculate the ASV? Number of legs into pi by 4 into d square, where d is the diameter of the stirrup. Here you can use 2-legged, 3-legged, 4-legged stirrup, and if the stirrups are not sufficient, you can use the bent up bar also. See, this is the bent up bar in addition to stirrup. The stirrups may be in inclined position also. So, but generally, vertical stirrups are provided. Then we solve one problem of design of shear reinforcement in the lecture number 9. Now in today's lecture, that is in lecture number 10, we will solve the second problem of design of shear reinforcement. Now in the second problem, it is given that a beam 230 mm by 380 mm effective. So I will simultaneously write the data. B is given as 230 mm, effective depth small d 380 mm. It is subjected to a factored shear force of Vu 80 kilonewton. The beam is reinforced with AST 3 bars of 16 mm diameter, then Fe 415 and M20 are used. Then design shear strength of concrete, that is tau C, is given as 0.53 MPa. This design shear strength tau C we always find from table number 19 of IS code. This tau C depends upon grade of concrete and percentage of steel. But here there is no need to use that table because direct value of tau c is given. And what is asked? Find the spacing, determine the spacing, find spacing of two-legged 6 mm diameter vertical stirrup. This is the requirement. Now, to start with, we will find first the tau v. The first step, nominal shear stress. Step number one. This is the solution. Step number one, find tau v, which is nominal shear stress Vu upon Bd. Bu is 80 into 10 raised to 3 in Newton divided by 230 by 380. So if you calculate this, you will get 0.915 Newton per mm square. Now in the second step, we check whether this tau v is not greater than tau c max. Tau c max depends upon grade of concrete and it is given in table number 20 of IS 456-2000. Tau c max is 2.8 Newton per mm square for M20 grade concrete. This is given in table number 20 of IS 4. Now as tau v is not greater than tau c max, that means 0.915 is not greater than 2.8, it is okay. Otherwise, we will have to revise the section, we will have to increase the size of the section. But here tau v is not greater than tau c max. Then step number 3, here we calculate tau c, that is the design shear strength of concrete. I will repeat, it depends upon grade of concrete and percentage of steel. The table number 19 gives us this value, but here as this is an exam problem, the value of tau c is directly given as 0.53 Newton per mm square. Now as tau v is greater than tau c, we will have to design shear reinforcement. Shear reinforcement. Now let us calculate what is the shear force to be taken by shear reinforcement. Step number 4, we will calculate Vs. Vs is what? Shear force to be taken by shear reinforcement. So Vs is equal to whatever is the total ultimate shear force minus Vc. Vc is what? Vc is the shear force taken by concrete. So this 80 kilonewton ultimate shear force will be taken by some part will be by concrete and remaining part will be by shear reinforcement. Now Vc is equal to tau CBD. See, this is stress into area of concrete. Stress in concrete, shear stress in concrete into area of concrete. So we see we got tau c is 0.53 into 230 into 380. So we will substitute the value of Vc here and we get shear to be taken by shear reinforcement is 33678 Newton. 33678 Newton. Now we can provide stirrups and bent up bar, but in this problem the question is find the spacing of 6 mm diameter stirrups. So no bent up bar, because see this Vs will be taken by stirrup and bent up bar actually. But here no bent up bars is provided or bent up bar not provided. I can write. So whatever is the shear force to be taken by shear reinforcement will be taken by stirrups, that is VUSV. So VUSV, that is the shear force to be taken by vertical stirrups, is equal to VS is equal to 33678 Newton. Now as it is mentioned that use 6 mm diameter two-legged vertical stirrups of AP250, because 6 mm is available in for AP250 only. So spacing of the stirrups SV is equal to 0.87 FY ASV D upon BUSV. So substituting the values 0.87 into 250 into substituting into, I'm sorry, the screen is very sensitive. 0.87 Fy is 250 into ASV 2 into pi by 4 6 square. See, this 2 stand is for 2 legs, and as 6 mm diameter bar is used, the area is 2 into pi by 4 6 square into D. D is given as 380 divided by this 33678, and after calculation what I will get 138.65 mm, say 135. Always round it to lower side, spacing always round it to lower side, so 135 mm. So this one value of spacing I got. Now this should be checked for minimum spacing, SV minimum, that is given by the formula 0.87 Fy ASV upon zero point 0.4 B. So if you substitute the proper values, 0.87 Fy is 250, ASV is again 2 into pi by 4 6 square divided by zero point 0.4 into B. B is given as 230. B is given as 230. So simplifying this, what I will get, spacing is equal to 133 mm. Again rounding it to lower side, it is 130 mm. So this is another value of spacing considering minimum shear reinforcement criteria. And now SV max, that is maximum spacing, should not be greater than 0.75 D. Here D is 380, 0.75 into 380. So I will get 285 mm. Further, this should not be greater than 300 mm. This is another criteria. So there are four values of spacing I got. Remember, always you will finalize the minimum of all, that is in this case 130. So final answer is spacing of stirrups, of course, 6 mm diameter two leg is 130 mm center to center. This is the final answer. I will repeat, always consider a minimum of all the values of spacing considering the all the criteria given by IS code. Now, let us consider the third problem. In the third problem, what is given? A beam 230 mm by 450 mm effective. So data B equal to 230 mm, small d 450 mm as it is given. Effective depth, it is subjected to working shear force of 70 kilonewton. So immediately I will find ultimate shear force by multiplying it by partial safety factor for load, that is 1.5 into 70, that is 105 kilonewton. Fe415 and M15 are used. Design shear strength of concrete, tau C. Yes, it is given directly, so there is no need for any interpolation from table number 19. Determine the spacing. Now, the spacing of what is required? Spacing of 8 mm TOR. See, this is TOR. Fe415. I will assume Fe415 two leg stirrups. This is required. It is similar problem with the previous one, that is second problem. Now solution as usual. First step, step number 1 is tau V, nominal shear stress Vu upon BD 105 into 10 raised to 3 in Newton divided by 230 is B, D is 450. So this is equal to 1.014 Newton per mm square. Now check this value with tau C max. Step number 2, tau C max. Tau C max is given in table number 20 of IS code. It depends upon grade of concrete and it is 2.5 Newton per mm square for M15 grade concrete. Now tau V is not greater than tau C max. That means 1.014 is not greater than 2.5. So okay, we can proceed now. Then in the third step, actually we find the tau C value, that is shear strength of given beam. Tau C, I will repeat, this depends upon grade of concrete and percentage of steel. It is given in table number 19 of IS code, but in the problem and the value of tau C is directly given as 0.504 Newton per mm square. Now as tau V is greater than tau C, shear reinforcement is required. Shear reinforcement is required. Now, what is the shear to be carried by this shear reinforcement? Vs, I will repeat, shear force. This is the shear force to be taken by shear reinforcement. This is our Vs value. Vs is equal to Bu minus Vc. Vc is again shear to be Shear taken by concrete, which is tau CBD. Tau C we know, tau C is 0.54, B we know 230, B 450, VU is 105 into 10 raised to 3 in Newton minus this VC, which is tau CBD. Calculate shear to be taken by shear reinforcement, that is 49.11 into 10 raised to 3 Newton. Now this Vs can be taken by stirrups. The shear is VUSV, and bent up bar. Bent up bar. The shear will be VUSB. B stands for bent up bar. But here there is no bent up bar provided. So whatever is the Vs is equal to VUSV. So VUSV is equal to Vs. So entire shear force to be taken by shear reinforcement will be taken by vertical stirrups of 8 mm diameter. Now spacing of 8 mm diameter is equal to 0.87 Fy, 0.87 Fy ASV into D divided by VUSV, which is 49.11 to 10 raised to 3 Newton. So here I will write 0.87 Fy 415. Here we are using AP 415 8 mm diameter for stirrup. So Fy is 415 into 2 for 2 legged pi by 4 8 square into depth is 450 divided by 49.11 into 10 raised to 3. So after calculation, I will get the spacing 332.6 mm. Always round it to lower side. Say 330 mm. This is one answer I got considering the 8 mm diameter and shear to be taken by stirrups as 49.11 into 10 raised to 3 Newton. Now check for SV minimum shear reinforcement, that is given by the formula 0.87 Fy ASV upon 0.4B. So we know that 0.87 into 415 into 2 into pi by 4 8 square divided by 0.4B, zero point 4 into 230. So after simplifying, what I will get 394.5 mm, say 390 mm. Don't round it to higher side because in that case the number of spacing will get reduced. Always round the spacing value to a lower side. So according to this criteria, the minimum spacing criteria, I got spacing as 390 mm. Now another check is SV maximum spacing should not be greater than 0.75 D. Here D value is 450. So 0.75 into 450, that is equal to, what I will get is 337.5, 337.5, say 335 mm. This is another value of spacing, and further spacing should not be greater than 300 mm. Maximum spacing should not be greater than 300 mm. Now we got four values of spacing. Always remember, finalize that value whichever is the lowest. Now in this case 300 mm is the lowest. So provide spacing of 8 mm torque at 300 mm center to center. This is the final answer. So after considering all the criterias of spacing for the syrup, you will finalize that value which is the lowest one. Remember. So this is the second problem. Now in the next lecture, we will solve the problem number 4, 5 and 6. So all the variety from the question paper will get covered. So thank you very much.